Let's do the properties for subtraction, multiplication and division, like same way what we did for addition. Alright, now for subtraction you don't have to worry about the commutative, associative, all those things, because you know it's not going to work. Right. So whenever we talk about subtraction now, so the next thing what you have is subtraction. So under subtraction, the first one is the closure. See, in closure, suppose if you have Z1 and Z2 are two complex numbers such that Z1 is equal to A1 plus I into B1, Z2 is equal to A2 plus I into B2. These are the two complex numbers. Now Z1 minus Z2 or Z2 minus Z1. The difference between any two complex numbers, they belong to the set of complex numbers. Now you might be thinking, what if I have an example like 2 plus 3i, 2 minus 3i, okay, something like this, or 2 plus 3i and 2 plus 3i. What if I subtract these two? Am I not going to get 0? So how is 0 a complex number? It's a real number. Yes, this is one of the very important questions which I want to answer right now. See here, 0, which is actually a real number, is also a part of a complex number. Okay, to give you a perspective as to how it can be represented. Now, all of you must have seen this particular diagram at least, you know, natural numbers, set of natural numbers. Then after that, after natural numbers, you have whole numbers. Next, after the set of whole numbers, we have integers. Then after integers, you have a set of rational numbers Q. Then after that, you have set of real numbers. A real numbers has all the irrational part, whatever, correct? Outside real numbers, then we have complex numbers. So technically complex numbers includes every number you know and every number you can think of. Everything is there in complex numbers. Okay, so the last part of it, this is the complex number set. Complex numbers includes everything. So when you say 0, 0 is also a type of a complex number. Otherwise, don't you think why we included additive identity as 0? It's a set. It's a type of a complex number. To give you even more better conclusion, see, 0 can be represented as 0 plus I into 0. See, it's in the form of A plus IB. So it's a complex number. Clear? So all real numbers are complex numbers, but all complex numbers need not be real numbers. Now this, I think it pretty much confirms that, you know, the closure property for subtraction, how it is true, correct? Okay, so Z1 minus Z2 is also equal to Z, which is a complex number. So subtraction is closed for complex numbers. This is first thing. Commutative, obviously no. Associative, obviously no. Okay, then identity, guys, you know it's not gonna work. So subtraction, the major part in subtraction is the closure, and whenever you have negative of a complex number. In the sense, suppose, let's say, you're going to have Z. Okay, Z is equal to A plus IB. Minus Z will be equal to minus of A plus IB. Fair enough? This is what we call as the negative of a complex number. This is a major part what we have in subtraction. The next thing what you have is the multiplication part. So next you have multiplication. Now in multiplication, first one, closure. Closure, again, Z1, Z2, two of them. The product of the two complex numbers, that also we have to calculate. Is it actually a complex number or is it something else? So for that, we do Z1 into Z2. A1 plus I into B1 multiplied by A2 plus I into B2. Multiply, you get A1 A2 plus I into A1 B2 plus B1 A2. I is common, right? Plus I square into B1 B2. What is I square? See, I value is root of minus 1. I square becomes minus 1, isn't it? So we get A1 A2 minus B1 B2 plus I into A1 B2 minus plus A2 B1. Now if you look at it, this is also in the form of Z is equal to A plus I into B, which is a complex number. So product of two complex numbers is also a complex number. Fair enough? This is the first property, the closure. The next one what we have is the commutative property. Okay, the next is commutative. That means you have Z1 into Z2 is equal to Z2 into Z1, which is quite obvious, so I don't have to worry about that, explaining it to you that what it is. Same thing is associative. Associative, Z1 into Z2 into Z3 is equal to Z1 into Z2 multiplied by Z3. Associative. Next is the identity. Okay, the fourth property, you can say identity. That means Z1 into 1 should give you Z1. Now you all know that 1 is also a complex number. So there exists an identity in the set of complex numbers, that is 1, where you multiply a complex number with that identity, then you are going to get the same complex number back. Fair enough? So existence of identity, we just proved that identity exists in set of complex numbers. Then the last one what we have is the inverse. You can say the multiplicative inverse. Now what do we have? Now this is a very important point to understand. Now in inverse, suppose you have Z1 is the complex number, then Z1 into something should give you 1. And it's quite natural that we have to multiply by 1 by Z1, correct? So Z1 into 1 by Z1 is equal to 1. So 1 by Z1 is what we call as the multiplicative inverse. And it's quite obvious that Z1 should not be equal to 0. Because it is, then you'll get denominator as 0, which makes no sense. That's why Z1 into 1 by Z1, so that 1 by Z1 is what we call as the multiplicative inverse. Fair enough? Now this is about multiplication. Guys, similar rules will be there even for division also. Quickly we'll finish off the division part. See, whenever we talk about division of two complex numbers, we take Z1 by Z2, where Z2 is not equal to 0. Now, to do the division part, we basically have to use the concept of conjugate and then solve it. Okay? And how we use the conjugate and all, you guys will see in the further videos. But Z1 divided by Z2 exists as long as Z2 is not equal to 0. Clear? So, these are the properties what we have for complex numbers. And in the next couple of videos, you will see how to solve problems and also a couple of properties of conjugate numbers. And as in basically complex numbers and complex conjugate. Okay, so we'll see those things from the next video.